Next super important question to pose here is, what kind of thing should I be comparing a series to? Well, the follow-up question that I have is, what does it look like? Kinda. If we're going to be comparing these series, then we're going to be given something and we're going to be comparing it to something else. So, series that we have had so far, does it look like a geometric series? Because that would be a great thing to compare it to. Does it look like a p-series? Now, frequently, when it comes to p-series, some of those could be technically in disguise. And they might be in disguise in the form of a rational function. So suppose that I give you a series like the sum from n equals 1 to infinity of n plus 1 over n squared plus 1. You can think to yourself, as n goes to infinity, how big an influence will that how big an influence will those plus 1s really have? Really, it starts to behave like n over n squared, which would be the same as 1 over n. In this case, I would say compare to this series. That, of course, being the harmonic series. Harmonic series is something that we know diverges. So if you can compare it to either a geometric series or a p-series just based off of the things that you see, you should be in pretty good shape. To give you an example of one such problem, I would like to consider the sum of n equals 1 to infinity of 1 over n plus 2 to the n. You'll notice that depending on which of these terms you choose to ignore, this could potentially look like the harmonic series, or it could potentially look like a geometric series. So let's call this possible comparisons. We could try comparing this to the harmonic series, or we could try comparing it to the geometric series 1 over 2 to the n. With that in mind, let's try out the first one. Let's compare to the harmonic series, which we already know diverges. Now it's up to you to decide whether you'd like to use a direct comparison test or a limit comparison test. If we try direct, then we would be comparing 1 over n plus 2 to the n with 1 over n. You'll notice that this denominator is larger, meaning that the series would be smaller. So what we're saying is we have a series that is smaller than a divergent series. Smaller than divergent means no conclusion. It could still be divergent itself and still be smaller. If we tried the limit comparison test, I'd be taking the limit as n goes to infinity of one of these over the other one. If I do similar algebra to what I did up above on the page, we could express this as n over n plus 2 to the n. This is an indeterminate form of infinity over infinity, so I'm going to apply L'Hopital's rule once. Differentiating the top and bottom with respect to n, numerator would become 1, and the denominator would become 1 plus 2 to the n times the natural log of 2. Now as n goes to infinity, this limit would be equal to 0. According to the limit comparison test, we are only able to draw a conclusion if this number is both finite as well as non-zero. So the limit comparison test just failed. Now, in the event that something fails, No big deal. Pick yourself up, brush yourself off, and try something else. We did have something else that we could compare it to, so let's try comparing it to that. I'm going to recopy the original series so that we have it. This time we are going to compare to n equals 1 to infinity, 1 over 2 to the n. Now the specs for this series, this would be considered a geometric series since we have a constant raised to an n power. The common ratio in this case would be 1/2. Every time n goes up by 1, each term is being multiplied by an additional 2 in the denominator. Now with that in mind, the ratio is less than 1, so this converges. If we wanted to try using the direct comparison test, we would be comparing 1 over n plus 2 raised to the n power with 1 over 2 to the n power. You'll notice that this term in the denominators is the same, but this has something additional added to it. So this one is going to have the bigger denominator. Bigger denominator means smaller fraction. We just showed that this thing is less than a convergent series. The direct comparison test works in this case. Therefore, by the direct comparison test, the series, sum from n equals 1 to infinity, of 1 over n plus 2 raised to the n power converges. Now, just because we got it right using the direct comparison test does not mean that you can't use the limit comparison test. In fact, let's go ahead and try it just to show that it's going to work out. We'll take the limit as n goes to infinity of ours on top and the thing that we're comparing it to on the bottom. We have a single fraction divided by a single fraction, so I'm going to change that to multiply by the reciprocal. That'll be 2 to the n power over n plus 2 to the n power. As n goes to infinity, this is going to be an indeterminate form of the form infinity over infinity, so I'm going to apply L'Hopital's rule. Take the limit as n goes to infinity of 2 to the n times the natural log of 2 over 1 plus 2 to the n times the natural log of 2. This is still an indeterminate form of the form infinity divided by infinity, so I'm going to apply L'Hopital's rule again. The limit as n goes to infinity of. The numerator is going to be the derivative of this, and the denominator is going to wind up being the derivative of the same thing because the 1 is going to cancel out. Really, though, it's going to be the 2 to the n times the natural log of 2 quantity squared, and 2 to the n times the natural log of 2 quantity squared. This number is 1. According to the limit comparison test, as long as the number that we get is both finite and non-zero, and this is both of those things, therefore, by the limit comparison test, these series sum from n equals 1 to infinity of 1 over n plus 2 to the n converges.